gases are flammable, liquids are not. So even if a liquid is labeled as flammable, you're not burning the liquid itself, you're burning the gas that comes off of the liquid. So this is a flammable liquid, but what you see catching on fire isn't the actual liquid itself, it's the gas.
That's so cool.
Okay. Here we go. So this is taking the air out and it's decreasing the pressure inside of the container. So what's happening to the marshmallows?
They're growing.
They're expanding. So the air inside is expanding, and when that happens, the volume gets larger. That's about all they do. What do you think is going to happen when I let the air back in?
They're gonna get smaller again. Look, they're already shrinking. Oh.
Exactly. So once they're jet puffed, you can't really put the air back in with this container.
So if you were
now
to
they're all
like,
shriveled up.
so if you were to like turn it on again, then they would just stay like that. They wouldn't get bigger again.
We did that third period. First period didn't even ask. And to my surprise, they do get a little bit bigger because we don't get all the air out of it.
Oh my gosh, it's like a magic
But
trick.
notice they're not getting as big as they did last time.
Yeah.
Because we removed a lot of the air from them. So that's about it. And they'll shrivel up even more this time.
That's like a magic trick.
So without the air in them, they taste really like chewy and dense. You wouldn't really want to eat these. Yeah. Okay, so make sure you write your observations down. Okay.
No.
So cans, aerosol cans, they're usually some kind of liquid, so the foam stuff is actually a liquid in here. And then when you spray it, it mixes with whatever gas is contained in there. This one has propane in it, so it mixes with the propane to make it foamy. So here we go. Now this one will keep going, but I borrowed this and I don't want to make a giant mess, so I'm not going to let it come out of the cup. But it would keep expanding, and then kind of like the marshmallow, it's going to go back, whoa, it's going to go back down. However, the foam kind of sticks to the cup. So if you look down, you can see most of it's at the bottom. What you're seeing is just what's stuck on the sides.
Oh, that's so cool.
So that's pretty much what it looks like before it comes out of the can and mixes with that gas. So keep in mind the size of it right now. So again, the pressure is decreasing. Now the amount of air that I put in the balloon is not changing, but remember those gas particles are expanding. So it's making the balloon bigger. Now this one kind of stops here because it covered up that little thing that sucks out the air. So if I leave it on too long, it'll break this. But it would keep going, and if it were a big enough container, we could fill it up big enough to pop it, as long as it doesn't cover up that nozzle. Well, if I would keep it going, that might happen, but again, that also might break.
What is the thing that you keep undoing underneath of it?
This is just what lets the air back in. So here we go. So did the size of it change from what it started as?
No.
No. So why did that happen this time and not the other times?
Because it's contained.
The air is contained in the balloon. The air cannot escape from the balloon.
All the air that was removed is inside the container.
Yeah.
It's more suspicious when you try to prove it to us. It's assume.
Alright. So before we do this one, we kind of have to talk about atmospheric pressure a little bit, and then we'll fill all this in after. But do you guys know much about the atmosphere's pressure?
Yeah, we always.
Talking about like the barometric pressure.
It's very similar to barometric pressure because that's how they measure it. That's how they measure atmospheric pressure, yes. What'd you say? Okay, so there is 14.7 psi, or pounds per square inch, of pressure pushing down on us all the time. What creates that pressure that's in our atmosphere?
Gravity.
Not just gravity, though.
It's the one in the air.
The gas, the air. So gas particles, remember, they move around, they have lots of space between them, they bounce off of things, they collide with things, and those collisions are what cause the pressure that can't really feel it too much, but to us it's like gravity. So we can't really feel gravity unless we're trying to overcome it, right? Same thing with pressure. They both kind of work together to keep our atmosphere in place and to keep us on Earth. So, what would happen if I hit this without paper on it? It would fly, right? Physics. Newton's third law. For every action,
There's a
equal and opposite reaction. But this piece of paper has enough gas particles bouncing down on it right now, very, very fast, that it has enough pressure to hold this paint stick in place so I can break it. You may want to go to the other side real quick, just to be safe.
Right, that's an
That's and just pay attention. I usually don't have it go too far, but you never know. Better safe than sorry. And I'm hitting it down here on the end, so just pay attention to where it breaks.
That broke twice.
And I really didn't hit it that hard, did I? It more has to do with the speed of it than how hard it gets hit. So the speed I have to kind of keep consistent. Look, it stayed under the paper. Now usually I get more of a dent than that. But normally you can see like there's an indentation in the paper from it holding the stick down. That one worked really good though.
No, pencil.
Pretty much broke in half, right?
Mm-hmm.
And it pretty much broke where the table was. And I hit it on the end.
Do a pencil.
If we have time, we already might not get through number 8 today. So I kind of cut the lid off and put a screen on it to take this one up a notch because you've probably seen this trick before. Just to prove it, I can pour it out and everything. I'll fill it up in here without removing that screen. So it's about half full. And this one actually works by creating another vacuum. Not the same type of vacuum as the vacuum pump, but when I flip this over, the pressure on the inside, so the air on the inside, has the same pressure as the air on the outside, which holds that card in place. So think of the card as being like sucked up. Now, you've seen this before, you've never seen this. So there's still a screen there, I can touch it. This has to do with the special property of water. So we'll get there in a minute. But right now the water has a force on this screen. They kind of like line up and hold hands like Red Rover. You know that game, Red Rover?
Mm-hmm.
So as long as I keep this very balanced, did you see it?
Yeah.
It will stay in place. But if I unbalance those forces, comes out.
You turned it, didn't you?
I did. I tilted it just a little bit. So if I would have done that while I was walking around, water would have poured out everywhere.
Mm-hmm.
All right. So for that special property, you can face them to see who can blow up their balloon the most. It has nothing to do with speed, so don't make yourself pass out or anything. Go ahead. Don't be shy.
Just take the balloon out.
You can put your mouth over it. I put that's clean balloon. I put the
not supposed. The air pressure on the inside that doesn't make that wood. You can't.
Okay, you're just not blowing hard enough. I was trying to give you the easy one because you were sick. All right.
That's not possible.
Okay, this one's not possible. That one is because I have a hole in it. But you are sick, so I'll give you that. Okay. So Damien, 1.
Wait.
Why couldn't you blow this up?
Because if you put it allows the air to escape through that way, and if you try to add more pressure, it's gonna push it back out of the balloon.
Exactly. So there's already air in this bottle, right?
Mm-hmm.
Pressure inside this bottle. Can't blow up that balloon unless some of the air comes out. And we're gonna let it heat up.
Oh.
And I'm gonna try this a little differently because the 2 other times I did this today, it was hard to screw on the cap once it got hot. And I tried using these and that's just not enough finger movement. So we'll try it without the lid on there. I usually heat it up like this. We'll see what happens. Now this one does take a few minutes because the water has to start boiling and you have to see a bunch of steam. So I don't know if you can see there's a
Oh, I see
little
it.
bit coming out right now, but we have to see this is where it gets tricky. So even just sitting it on the counter, it's cooling down.
It's gonna give another go with that nightstick.
It hit a hot spot and started boiling. The water started boiling again. Okay, so the can crushes, but let's explain why.
Have you done it
Yes.
before?
The hard part about the pencil is the paper doesn't lay flat.
Is it still crushing?
And the flatter the paper is, the better this works because air can get under it if it's not flat. So let me,
Is the can still having a reaction?
it's still cooling down a little bit, yeah.
That's fine.
I'll try that and see if that goes.
We used to have this thing where we make it seem to where you would like. Basically, you would put a bottle in a freezer and give it a roll, and then you take it out and you put a coin over the lid, and feel it with your hands, and when it causes it with the coin, you shake off the top, just like drop this down.
Okay, you may want to watch out. The pencils are usually more unpredictable.
It's okay, I got you.
And I have to be more accurate with this weight. It did work, yes.
Whoa.
Okay, so this one for sure, I know I kind of pressed it down, but you can see the indent a little better in the paper. And that's pretty much where it was on the end of the table. Did that get 2 pieces?
Yeah, it did. Just raw power.
All right.
Is it gonna explode?
Is it doing something?
Oh, come here, look inside the balloon.
You left a little bit there.
No. You see the bubbles forming all around it?
Oh, yeah, because there's.
If you come up here and look at this,